So we left off last class period looking at graphs of exponential functions, and now we're going to look at solving exponential functions. Solving exponential functions, we're going to try, and then this is not always possible and usually not possible, but we're going to try to manipulate the bases to be the same. And if we can do that, then we can use this rule. And the rule states that if you have some b raised to the x power is equal to, let's say, b raised to the y power, then we can say x is equal to y. Our base, when we're doing this, our base has to be greater than 0. Our base can't be 1. If those cases need to hold true. So let's look at an example. So let's say we had 1 over 25 raised to the x power is equal to 5 raised to the 3x minus 1 power. And so we want to try to manipulate this to have the same base. I noticed that 25 we can rewrite to have base 2. And so we could go over here and use our rules of exponents. So we have 1 over 5 squared raised to the x power equals 5 raised to the 3x minus 1 power. We can bring that 5 squared up into the numerator by changing the sign of the exponent. So this is the same thing as 5 raised to the negative 2 power raised to the x equals 5 raised to the 3x minus 1 power. Rules of exponents, power to power is multiplication. And so the left-hand side we can rewrite as 5 raised to the negative 2x power equals 5 raised to the 3x minus 1 power. So we've manipulated this so that the bases are the same. And so now we can use that rule and set the exponents equal to each other. So we have negative 2x is equal to 3x minus 1. So let's subtract 3x on both sides to get x to one side of the equation and the constant to the other. So we get negative 5x equals negative 1. Divide through by negative 5, we get x equals 1/5. Let me pull another one. So this next example, we have 9 raised to the negative x plus 25 power, which is equal to 27x. So again, we want to manipulate these bases to be the same. I cannot manipulate base 27 to be base 9, and then vice versa. I can't manipulate 9 to be base 27. But we can rewrite both of these as base 3. And so 9 we could rewrite as 3 squared, and then that's all raised to the negative x plus 25 power is equal to, and 27 is the same thing as 3 cubed raised to the x. So again, power to power is multiplication. So distribute that 2, we get 3 raised to the negative 2x plus 50 equals 3 raised to the 3x power. So now we can just set our exponents equal to each other and solve for x. So negative 2x plus 50 equals 3x. So get x's to one side, we could add 2x to both sides. We get 50 equals 5x. Divide through by 5, we get x is 10. So what if it had been 9 raised to the 2x all times 27 raised to the x squared is equal to 3 raised to the negative first power. So same kind of idea here. We want to manipulate all the bases to be the same. I noticed that, again, that 9 and 27 can be base 3. And so let's go back and rewrite that. So this 9 is 3 squared, all raised to the 2x power, times 27, which is 3 cubed, all raised to the x squared power. Equals 3 raised to the negative 1. Again, power, rules of exponent, power to power is multiplication. So we have 3 raised to the 4x power times 3 times x squared, so 3x squared equals 3 to the negative 1 power. Same base on the left, and there's multiplication in between. So that means that we're going to add our exponents. Those are not like terms for our exponents, so we're going to leave it as a sum. So this is 3 raised to the 3x squared plus 4x equals 3 raised to the negative 1 power. So now that the bases are the same, we can set our exponents equal to each other. So we have 3x squared plus 4x equals negative 1. So this is a quadratic, so we want to get everything to one side. So we have 3x squared plus 4x plus 1 equals 0. We want to factor it. Let's see. So 2 things that multiply to 3 that would add to 4, which would work. So let's just do 3x squared plus 1, not 3x squared, 3x. And let's do x plus 1, and let me just check. So my middle term, that's going to be a 3x plus an x is 4x. And my last term, 1 times 1 is 1. And 3x times that x is 3x squared. So we got it right. So set each factor equal to 0. So we are looking at when is 3x plus 1 equal to 0? Well, if we subtract 1 and divide by 3, we get x equals negative 1/3. And x plus 1 is 0 when x is negative 1. So there's 2 solutions to that equation. So our next example, e raised to the x squared is equal to e raised to the 3x times 1 over e squared. And so we're going to look at this. We want to manipulate the bases to be the same. They are the same, but we just want one base of e on the right-hand side. So let's rewrite this 1 over e squared, bringing it up into the numerator. And so the left-hand side, we still have e raised to the x squared equals e to the 3x. And now this is going to be times e raised to the negative 2 power. Again, we want to use rules of exponents. So same base on the right-hand side, we're going to add our exponents. So 3x plus a negative 2 or 3x minus 2. We can now set our exponents equal to each other. X squared equals 3x minus 2. Get everything to one side, x squared minus 3x plus 2 equals 0. So factor it, x minus 2, x minus 1. So x minus 2 is 0 when x is 2, and x minus 1 is 0 when x is 1. So this is so much fun. It's just like manipulating kind of how are we going to manipulate this to work out and fall out nicely? I hope you guys are getting as much enjoyment out of this as I am. Okay. Let's look at another example. This example is giving us information, and let me just state it in here. It says, suppose that f of x is equal to 2 raised to the x power. So we have f of x is equal to 2 raised to the x power. And we want to know what is f of 4 and what point is on this graph of f. Okay, that's not too bad. So what is f of 4? Well, all this is telling us to do, right, is to go in and plug in 4 wherever we are seeing an x and f of x. And so we got 2 raised to the 4th power. So we got 2 times 2 times 2 times 2, which 2 times 2 is 4, times 2 is 8, times 2 is 16. So we get back 16. The next part of that question was, what is the point? The point's going to be 416 on that graph. Part B says, if f of x equals 1 over 16, what is x and what is the point on the graph of f? So if f of x is equal to 1 over 16, find x. Okay, so we're just going to set our equation 2x equal to 1 over 16. Manipulate our bases to be the same. We just saw that 16 was 2 to the 4th power, so we have 1 over 2 to the 4th. Bring that up into the numerator and make that exponent positive. So we have 2x, 2 raised to the x power equals 2 raised to the negative 4th power. So in here, we can see that x is equal to negative 4. So the point is going to be negative 4 1/16. So exponential functions a lot of times are representative of a lot of application problems. And so let's look at the following example, and this is on drug medication. It says the function dh equals 5e raised to the negative 0.4h can be used to find the number of milligrams d of a certain drug that a patient in a patient's bloodstream 8 hours after the drug has been administered. How many milligrams will be present after 1 hour and after 6 hours? So we're given what the equation was that gives us how much drug in milligrams is left in the patient's system. And so we have D here is equal to 5e to the negative 0.4h. And we wanted to find out how many milligrams was in the bloodstream after 1 hour. So when h equals 1. And we also want to see what's happening after 6 hours. So this is basically just a calculator exercise. We're going to plug in 1 wherever we see an h. So we have 5e to the negative 0.4 times 1. And so we have 5e raised to the negative 0.4 power. I'll bring that up in a minute and approximate that a calculator, but let's do this also. So we have D is equal to 5e to the negative 0.4 power, all times 6. Okay, so now all we're doing is, and I plugged in my equation into Desmos. And so now I can evaluate this at any value I want. And we wanted to figure out what's going on when we have H is 1. And so D of 1 in here, I get approximately 0.52 or 53 milligrams. And if I want to see what's happening after 6 hours, we're left, the blood medication left in the bloodstream is approximately 0.02 milligrams. This was approximately 0.53, and this was approximately 0.02. Okay. Okay, so that brings us to our next section. Let me start a new video for that.